Hello everyone, thank you to be here. So today we're going to present a really nice use case about the hybrid search. But first, I would like to ask you, who is actually running a search engine with hybrid search technology on production? Okay, quite a few people. Yeah, of course, Radu, you're with me. So you're going to find in this presentation some lesson we learned during the process that brought us to bring hybrid search in production. But first things first, we're going to present ourselves. We are a French-based company called Adeline. We are experts in search technologies. We are consultant, and our expertise gravitate around mostly three products, so Elasticsearch, OpenSearch, and Solar. And also, we develop our search engine called all.site and a super powerful engine for e-commerce called HU, or Ad in French. As I said, we are consultant. We are search consultant, and with Radu, my colleague, we are search consultant at the French National Audiovisual Institute. So every time I do a presentation about the French National Audiovisual Institute, I say that it's called INA in French, so Institut National de l'Audiovisuel, and I like to say I like to call it INA. Otherwise, I lose too much time saying the French National Audiovisual Institute. That's the third time I say it. So what is the mission of INA? The mission of INA is the French. Essentially, it's a French archive. So the mission is to preserve the audiovisual cultural heritage of France. We do this through the collection of video and audio from 106 radio and television services that are collected 24/7. So we have around 29 million hours of video and audio. We are also collecting photos for a total of 2.3 millions. And this is just a part of the job, because we have also not traditional media that we collect, like archived websites for 100 billion URLs, as you can see, and also tweets from Twitter, that now is X, but well. So you may wonder, okay, you are collecting all the web, all the tweets. No, we are actually collecting everything that is related to the French heritage. So, for example, we are collecting tweets from certain French big personality, like the President of France, or tweets with a certain hashtag. We are not collecting all the web, of course. And we are collecting also other not traditional media, even if they are becoming traditional media, like Netflix, for example, and podcasts. So with my colleague Radu, oh sorry, I went back. Problem. With my colleague Radu, we were part of a team that works into INA data lake. So we saw already the amount of data we have to manage, but this is just the visible part of the iceberg. Then we have all the metadata. In the data lake, we are dealing with this part that is under the water, so the metadata part. And this is used to describe video and audio for a total of around 60 million documents. So we talked about the data, the metadata. To get more, to understand better the context of INA, we need to talk about the data model.
Yeah, so the data model is a key aspect in our solution. So while we'll present our journey with implementing the search solutions, we'll try to share with you the different challenges that we faced. Some of them are more complex, some of them we managed to find alternatives. But what was important for us in different iterations that we had in our implementations until we got to the hybrid version of our search is that the data has a certain specificity in our context. And it's important in this introduction to have to understand that the modelization of the data basically is based on a functional view, the way that the stakeholders and the documentalists are organizing their data. So all that metadata of describing different heterogeneous content has a very strict way of being organized. So in this slide, it's important to see the three different viewpoints, different aspects of the data. The first one is related to the content. So in an abstract way of considering all the content. We have, of course, the video and audio, which is collected 24/7. We have, for instance, the daily news, different live, different replays, movies, series, even publicity. Everything is recorded and stored. But not only, there are also archived images for the last 25, 35 years, different photos with their stories related to them, screenshots, and also text, press releases, books, etc., etc. So this is, on the left side, pure content. But considering that all this content is stored for a long time and it's preserved, the purpose of the Institute is to preserve it a very long time in a physical format. On the other side, you have the media. So the media point of view represents the different system of organizing the physical support, the files, the MP3 files, archive files, and even the physical tapes, VHS, and Betacam. So as the technologies evolved over the years, the Institute kept all this in their archive. So this is also, there are important informations that are related to the media. And then all together, in the middle is the concept of event, because several entities, several parts of the content can happen iteratively throughout a certain period or continuously. Each and every day you can have your news session at 8 p.m. on your favorite national channel, for instance. So the concept of event, it's important because the documentalists, the archivists, when they are looking for a particular information or a particular social event or political event, they have to know this representation of the moment in time when different things happen. The moment when a content was produced, the moment when it was broadcasted, several broadcasting events, the moment when the content has been digitalized, because some of the old archives are still in a tape version, and they were recorded also in a digital format. So these are the three points of view, and we call them entities in an abstract way. They are complex relations in between them. But what's important from a search perspective is that for us, and we believe that it's a very interesting use case, not only the volume of the data, because we mentioned there are over 60 million documents, but also the complexity of the relations in between in our first version of the search engine, the first challenge was to be able to modelize these relations. Of course, everything, all the metadata is stored also into a relational database, but we transpose everything into a search engine in Elasticsearch and trying to flatten the graph of the data in documents, JSON documents that can be queried and searched in the system. Now, it turns out that this metadata is very heterogeneous in the sense of the completion. Some elements are more detailed than others. Some content, they have a free text associated. They have a title, they have a collection that they belong to. For instance, the daily news is related to a collection of news related to a certain channel, and so on and so forth. This information is automatically added or manually added when the content is archived, but it also it's a whole procedure of archiving and curating the data. The documentalist, the archivist, there is a whole team with very specialized on organizing the data, and they try to do as much as possible in adding more metadata so that the content can be more easily searched and identified according to different needs. So that's fine when you have this information, or when the documentalists have enough time to go through all this huge amount of data, and they have enough information to add into the system. But this is not always the case, and as this is a very tedious work, and it takes lots of time, and the information keeps coming and coming 24/7, and the number of channels, the number of broadcasters keep increasing, it becomes more and more difficult to be able to cover all the data, and some of the collections, some parts of the collections are somewhere deep down at the bottom of the lake, and it's basically it's impossible to be able to access them. So this is when we introduced our second iteration of our search solution, because we started with a lexical search. It proved to be effective on this semi-structured data, as I mentioned, as a graph model, and on the curated data that is already available. We build different versions of full-text search, advanced search, auto-completion, different filters, different aggregations, nested aggregations, you name it. So different complexity at this level. But applying all these methods in the lexical search, we realized that those golden nuggets in our collection are impossible to detect. So how do we do that? For not curated data, the logical step forward was to try to give more semantic and to produce some automatic annotation, and to try to build a semantic search solution on top of that.
Yeah, and we, as Radu said, there is a part of our collection, thank you, that is not discoverable. We can't find it because essentially we don't have enough metadata to cover it. Like 43% of our collection has not enough metadata, so it's impossible to actually find it. So we thought to pass through generated from AI generated data using a model like the one that we're gonna see for creating transcriptions, and we said to ourselves, maybe this is the best way to try to capture the content of our video and our audio and be able to search it. We don't have only generated data like transcriptions, but we have also other model for other kind of data that we use that use AI to be extracted from, like for example face recognitions. We also have name entity recognition, but for this use case we're gonna specifically see how we do with the transcriptions. So some word about the transcriptions. I want to give some credit to the INA is a big institution. There are many departments. I want to give some credit to the AI department that did this amazing job. So we have, of course, Whisper Large, that is one of the best model for generating transcriptions. We also have, really important, we also have diarization. So we are creating speaker tones. We exactly know who's speaking and in which moment. So we essentially created segments of our transcriptions. We are stocking them into different formats, and then we are using Elasticsearch for the search purpose.
Yeah, so about Elasticsearch, it's, as I mentioned, that was the first iteration. It worked fine for lexical search, another important thing is to mention is that we have a certain framework, a workflow that is already set up, a certain CI/CD workflow that is already in place, different environments from development, integration, production. The goal was to build something on top of what's existent. Somehow you can see it as a constraint or a legacy, but on the other hand, it's the benefit of being able to pass very quickly from a proof of concept to a solution ready for production. And this is what happened for us in a relatively short span of time. We managed to really index everything, or well, a part of the collection, and to prove that it works on the production environment. So just all that to mention that we have Elasticsearch currently, but all the options were on the table, and as things are moving fast nowadays, we are interested in exploring other solutions and to try to compare and to see if some others they perform better. But for the moment, that was not the goal of our project. We really based our implementation, our study on a framework that was currently used.
And so we naturally decided to use Elasticsearch for also not only the lexical search part, but also for the semantic search. And it works quite fairly well. So we are sticking with it for the moment. Well, we're going to do a short recap about how semantic search works. So lexical search, as we know, is based on keywords. Semantic search is based on meaning. The idea is, of course, that we are giving another transforming our document into vectors to extract the meaning. Well, we have already seen this schema, this nice schema. So essentially, we have a part where we have our document, we are indexing, we are putting them into a vector space. On the other side, we are taking the user query, we are vectorizing it, and then we are comparing it into the vector space with our documents to get the most similar result. So, as we know, there are two possibilities for semantic search, sparse and dense vectors. We went for dense vectors, and I think it was the best choice for our use case. But then, as I said, we had many challenges to face. So
yeah, that was the moment of scratching head and okay, we use vectors, straightforward. We won't invent anything. We try to pick up some of solutions, but the question is which one? And it's not only one question; there are several of them. So we are trying to summarize different stages of our analysis and how we advanced one step after the other. So the first one was to think about the embedding model, which one to choose. Is it only one? Is not really reasonable, because the models, they change. You need to train another model, or there's yet another one that shows up. It would be interesting to try another one. All that, you can do it in a proof of concept project, but when you want to put all that in production and to be able to switch quickly from one to another, then you have to anticipate and to build an architecture that allows you to do that. So, and eventually to be able to compare different models. So that was one first dilemma. Then the second one, and essentially, which is still not finished, and we still work on that, is which chunking method. We have some text, we have the transcriptions. We can, initially we had the naive approach to use paragraphs or speech turns, or so different ways of cutting and chunking the text. But then the question that comes is which impact you will have on the semantics. The size of your chunks, is it large enough, or maybe it's too large and then the semantic changes, or too short and then you cannot extract any semantics. So that's very, in our opinion, a key question that can have important consequences on the rest of the project. And then we also had to keep in mind that we want to go to production. We have on-premise Elastic cluster managed by our data operators and specific teams that put in place and manage the production environment. So we had to think in advance about different requirements in terms of physical machines. The first question that comes is how much memory you should have. But this is related to the volume of your data. This is related to your model, your vectors that you are going to produce. Are you going to find some optimization, some good methods of compression? And if yes, which one would be the best? So all that having an impact on the physical requirements of the infrastructure, that was part of the analysis and an important aspect to keep into account. And the last but not the least, the question is, are we able to combine search score from these two different visions? So we'll talk about that a bit later on. So the first part with the model. How did we choose the model? Of course, it doesn't come as a surprise. The most part of the collection is in French, but not all of it. We are not all 100% French, so there are parts, different documentaries, different parts of the visual content that are in English, of course, Italian, Spanish, different languages, but mostly we had to adapt and to orientate our choice towards a French model that provides a fairly good accuracy and precision. I like to take this example of that thing that you type on. I won't pronounce in all the languages because it definitely won't be correct, but at least you can see that the spelling, it's similar in most of English, German, Portuguese. In French is particular. In French, it's not computer, it's ordinateur. So that gives you the taste of applying the right model for the right language. Of course, in lexical search, there are lots of hints and techniques to go around using synonyms, using different analyzer, and organize your data to use different analyzer for the same piece of text. But when it comes to semantic, it's important to have the right model. Then I just took a screenshot from Hugging Face, and the first information that you get there, you see you have more than 1 million models available, almost 2 million. So for someone that is not really specialist in this field, which is our case, and again, we have to give credit to the other teams that they tried to compare different models. It's very confusing. So it's an important decision, and thank you. It comes along with our idea to have a flexible solution that can eventually accommodate different models. So I won't be able to give you details which one and why we chose this one. Just a general idea. It's an embedding model based on Camembert, which is the French version of BERT, and proposed by a French team of researchers back in 2018 or 19, if I'm not wrong. And the implementation of this model that we have chosen is proposed by La Javanaise, a French company, and more precisely, the model is called Sentence Camembert Large. So it's a pre-trained corpus of French English with a dimension of vectors of 1024 and is limited to 512 token input.
So yeah, this is one of course, a limitation of any model for embedding as an input limit, so we need to do chunking. We had a few options. So the first option was to start with the speaker term-based chunking. So we were using a diarization. We were taking segments, so chunks in this case, and we were creating embedding from them. There were essentially two problems. So the first problem is that vectors are really expensive, and we were generating too many. So we were having around, I wrote 1 billion, it was it was 850 million around. But you need to imagine that we were considering only the speaker terms from 2012 to 2024, and it's always increasing, because you're always recording things that are coming on television or on radio, and you have also to transcribe past events, so everything before 2012. So it's gonna always be more. As I said, well, this is the formula to calculate the required memory for having a proper vector search with good performance, at least in Elasticsearch and also in OpenSearch. We're using a model that has 1024 dimension, and at the beginning we were using a basic flow32 element type. So at the end we came up with the calculation, as you can see, and here you can see the part that is dedicated to the hierarchical navigable small world, and it was just too much. I mean, it was you see, a lot. And when you consider that in Elasticsearch, this as the space that is allocated for vectors is off heap, and so in general configuration, you have 50% of your RAM off heap. It means that you actually need twice this to store the actual amount of vectors that, I repeat myself, they are just from the 2012 to the 2024. So, I mean, probably too much. So we did, of course, we used the quantification. As we know, quantification allows to reduce the memory footprint. We tested, and we tried to validate all the different technique. You can see the difference from the flow32, where you have around 4 terabyte, and the integer 8, where you have 1 terabyte. So we saw that some compression technique led us to lose too much quality, so we had to find a compromise, and so we decided to pick the int8 compression. Then, once again, there were two problems. So the first problem that we had too many we have too many vectors, and so it generates too much data, and we had to deal with that. But the other problem that the transcriptions were short. So as you can see in this case, this is actually a screenshot I took from our document. Well, you can notice that we have different characteristic associated to the segment. For example, you know that a man is speaking. You can see, of course, the text. You can see, of course, the duration and also the timestamp. I want to focus on the text. I mean, when we are vectorizing this thing, CSA, I mean, that means that's it. This is it. I mean, it's really hard for the model to extract a sense from it. So that's not really a good meaning for us and for the model. Even us, we don't know what this segment is talking about. And so we had other options that we tried. And in this moment, we are actually using an optimized size chunking. So as we said, the maximum token accepted by the model are 512. And so we are just cutting every chunk to have a maximum 512 token. Of course, we are cutting it dynamically to not to lose content, or to not to cut just in the middle of the phrase. This is right now, while I'm speaking, but in the future, in a few months, and the AI team is already working on it, we are going to use semantic chunking. So we're going to cut our transcription based on thematic. And these two options of chunking, they're going to give us the possibility to reduce our vector base from around 1 billion to 55 million, once again, from 2012 to 2024. And we're using quantification with int8. So when we calculate the required memory, we found out that at the end, we just needed 55 gigabytes of RAM.
Yeah, so again, related to the modelization of our solution, we knew that we are going to go through different iterations, but we wanted to fix at least the guiding principles. First of all, we knew and we wanted to have the modularity of the architecture, first of all, to fit into the existent, into the data lakes workflow, and to be able to interact with the other frameworks. Different models that are tried by different teams, we should be able to integrate them easily. So modularity was essentially from the beginning. Then the flexibility, to be able to keep the pace with changing models and new versions, and to be able to test them without too much effort and too much time of modifying everything and re-indexing things. And also we have to keep in mind the particularity of the data in itself, because it continuously changes. There are new documents coming, but there are some old documents that are being updated. So the updates are quite frequent. So again, the flexibility, it's a key point on that. And of course, the scale, because this is where the problems show up when you have a small, you take a small part, a small subset of your collection, you try it on, you see that everything works fine, and then you try to go up with an order of magnitude, and then things are degrading very quickly. So scalability was an important point. So these are the three main principles, and then a couple of words about the modelization of the data, or maybe an architecture of our indices and how we iterate through different options. So the first approach was quite straightforward. We put everything into a single vector, a single index, sorry. We have transcriptions, so the text part. We have the embeddings, of course, identifiers of the fragment, also an identifier of the support, of the video support, be it a file or the reference in the collection. And what is important also is to give, as we saw in the previous example, to give the exact moment in time when the fragment starts and the fragment ends. So this way, we are able to uniquely identify each chunk, each fragment. Easy to implement. We just throw everything into an index. The workflow was already ready because we index different other text content. So that was the easiest part. The problems with this solution are twofold. The first one is changing the updates into the text. That means we have to consider the updates into the index quite frequently. So that leads to a sparse index and also an extra load on the indexing process. But even worse than that, when we want to change the model, that means we have to change all the documents in this index because all the vectors are changed. And also for different other reasons of identifying and chunking and doing joins in between the support and the content, the transcriptions, we had a risk to have duplicates. So then a second idea, a second approach was to separate things and to have a multi-index approach, which means what? It means we have a separated index for the transcriptions and another one for embedding, or eventually multiple indices for embeddings for different models. The separation is clear. The scalability also is provided because it's as easy as adding an extra index, in quotes, but anyway, it's more flexible and more easy to put in place. The problem that comes with that is that the search relies on aggregation, and we have to strictly monitor the performance when we do these kind of aggregations. So that's the challenge.
And of course, the second challenge was how do we combine lexical and semantic search? Well, as we know, lexical search with its algorithm has score that can range from 0 to infinite, essentially, while semantic search, of course, scores between 0 and 1. So did we have to choose any of the two pairs? No, we had to take both, of course, and we had to do hybrid search with the proper re-ranking. Reciprocal confusion is the main method used by Elasticsearch, but it's not available without license. So we couldn't do it. Also, an external implementation of reciprocal confusion is just not possible because since we are relying a lot on aggregation to, for example, find out the most pertinent video that contains the most pertinent segments, we are relying a lot on aggregation, and so aggregation are pre-calculated, and so if we want to use our backend to reprocess all the document, all the results, is just a mess. Then we have other methods. So min-max that also OpenSearch is using it its search pipeline, and A10 normalization. And so we decided to use these methods and to have our own implementation in Elasticsearch using, of course, script score. Once again, we use script score because we need to compute the document score before aggregation is calculated. Score is normalized only for the lexical search. So as you can see, We have the first part where you have the KNNN, where you have no, of course, normalization. We don't need it. And then we have the ATAN application of the normalization formula, where the lexical score is normalized. And then we are, of course, doing combination between the lexical and semantic using aggregation on a common ID term. Once again, we are not on a classical approach where we have a single index. You have to imagine we have multiple index where on an index, we have only the text, and on the other side, so the transcription, and on the other side, we have the embedding. The formula, as you can see, they are quite easy to understand. Now, the min-max has a little problem. We need a double API call to obtain the max score, because we need it for our normalization. So it's a bit harder to implement. The ATAN doesn't need for a double API call, but this distribution, as you can see, is quite different from the original distribution. As you can see on the y-axis, there is the frequency of document, and on the x-axis, there is the score. So the score remains essentially with the same distribution for the min-max, while for the ATAN, the score is messed up, and this risks to give, when we combine the score between lexical and semantic search, risks to give more importance to the lexical part. So we must maybe play with boost in Elasticsearch to try to compensate this difference. At the moment, we're using ATAN because it's way easier to implement with the script. In the future, we're going to use min-max. So this I already said.
Yeah, a quick word about the architecture. We are running a bit late, but just to mention different frameworks that we use and to show that the modularity is very important. So, for instance, for the AI inference, we use OpenVINO, which is an external microservice that is called before calling the search engine. As I said, we have an on-premise Elasticsearch cluster on the left side. On the right side, it's a screenshot from the application that initially implemented all the filters and all the features and options for the lexical search, and now there is a specific functionality for the semantic search. The search engine is implemented as microservices in a Spring Boot and managed by Kubernetes. And I wanted to go quickly to the last slide. Yeah, I'm sorry, we won't have the time to mention the evaluation, which is ongoing, but I wanted to emphasize on the takeaways. So maybe we presented a big picture with a big puzzle of different problems and different solutions, but I was trying to summarize the key points that we think that are valuable from our experience. So first of all, you have to consider to have a modular and flexible architecture. In our case, we reached this conclusion in doing multiple iterations. And it's important to be able to accommodate different models. So these are things that change very often, and it's important to have this possibility. The second one, in my opinion, is critical, is the chunking method, which applies, and you have to choose according to the specificity of your data. And to conclude, we concluded that re-ranking is difficult. The problem is essentially the structural difference in between the two ways of computing the scores. Evaluation is ongoing, and thank you for listening us, and we are open to discuss with you if you have any questions or you have any suggestions. Thank you.
Thanks a lot for your very interesting talk, Radu and Pietro. We do have a longer break right now, so I give you slack about the questions. Do you want to answer some questions?
Yeah, sure.
Yes, I see one here.
Thank you for the talk. You mentioned brief evaluation, so I don't want to spend much time on it, but just as a curiosity, many components and factors you've been showing affect relevance and affect the ranking of results. And given the scale of your problem, okay, it's in progress, but what's the strategy for evaluation? Because you talked about like billions of documents. And
I can give a short answer. The first conclusion, even without measuring, was that chunking was very important. So we started with speak turns, then paragraphs, then we went back to speak turns with different techniques. So that had a visual impact on the results. And the second part of the question, what's the strategy? And that's something interesting that we concluded, is that we cannot do a dynamic evaluation because we are in production, but we don't have enough users to have a feedback. It's not open to the public. It's open to a restrained group of people, the documentalists, the archivists, and they are not as many as needed. So all these methods of click-through rate, dwelling time, or so on, we simply cannot use it. So we turned towards a static evaluation with generically synthetic data. We created questions. We used an LLM to create automatic questions for some paragraphs. So that's the main idea. And then there's a process of filtering out the questions that are pertinent, that are relevant or not. And using those questions, we interrogate the system to see whether it finds the correct paragraphs. So that would be, in 2 words, the evaluation strategy. And it's ongoing. We are really working on that.
I also have one more online question for you. What were the problems with your test with BBQ or barbecue quantization method? Have you used oversampling the number of candidates for the retrieval?
So essentially, once again, this is a problem evaluation. We ended up that just integrate was the best compromise. And the number of documents for retrieval, this is a big issue because first we need to explain to the business how semantic search works, and because the business essentially wants to retrieve all the most possible result. So if they always want to retrieve more and more and more. It's quite weird, but it's like that. But we had to stick with a limit of course, retrieved documents. So we decided for the moment to stick with 1,000. So that's the limit we gave us, and the limit we gave also to the business. So once again, the search engine give you the possibility to choose between lexical and the semantic part. You can choose your weight. You can deactivate the semantic. You can deactivate completely the lexical. You can do hybrid search. Of course, when you do the hybrid search, you're going to retrieve, well, from the semantic, you're going to retrieve the 1,000 elements. And for the lexical, you're going to retrieve all the documents that are relevant for the lexical chosen algorithm.
All right. I see one more question, then I have to cut it. Sorry.
So you talked about normalization from lexical and vector search. Did you try to approach it with cross-encoding approach or something like that, which does not depend upon the base code written by lexical or vector engines in the hybrid search approach? So
wait, in the hybrid search approach,
So you were talking about re-ranking. So the challenges in the re-ranking when the score is written from lexical engine and the vector, because you have to normalize it.
Yeah, the lexical we have to normalize.
Have you tried cross-encoding kind of re-ranking, which is not dependent on the base score of lexical and vector?
You mean, okay, using cross-encoders, you mean to re-ranking? No, at the moment, it was one of the possibility, but at the moment we are keeping it, well, it's not simple, but we are trying to keep it as simple as possible. So we didn't try it yet, but it was one of the possibility that we studied so far. Who knows, maybe in the future. As I said, we also picked dense vectors. We may have gone for sparse one. Who knows, maybe in the future we're going to do, once again, an hybrid approach where we have a sparse model, a dense model, and a top re-ranker. I don't know. It's evolving, so who knows. Thank you.
All right. Thanks a lot for your questions. Thanks a lot for your talk.
Thank you.
Thank you.